the free body diagram and apply Newton's law. Let me start to work on this, so hopefully you can see this one clearly. So this one we have 2 degrees freedoms and designate by x1 and by x2. So here I simply take the free body diagrams on each mass block. Okay, so this is M1. And assuming M1 and taking the free body diagram in these directions, and let me try the other one, M2, how about here? Okay. So here, let me make up one. So assuming the M2, the degree of freedom M2 is larger than M1, then X1. So here, to be easier for us to sketch and the right amount of the force. So due to the equipment, the displacement here, this spring, due to stretch by X1, so that will provide the K1, X1, and the magnitude is in that direction. So when I draw the free body diagram, apply the force on here, not only I identify the magnitude, but also, based upon the assumptions of the displacement, I also impose the right directions of the force. Okay, so that is the key, and not to make any mistake in free body diagram. In a similar way, this is the damping. So the damping would have the C times x1 dot. Okay. Now we come to okay. So there's another force. So external force. Let me use color. So that is F1. So that representing is the externally applied force here. Okay, now we come to decipher the force from spring and the damper here. Okay, due to the assumption x2 is greater than x1, so this spring has been stretched. K2 spring has been stretched, and the stretch, that means applied to M1 here, that force must be equal to this. Direction is in that direction. Again, because based upon our assumption degree of freedoms, this spring has been stretched, so that force is that in that direction applied to this one. And the magnitude simply is the x2 minus x1, the amount of the loading produced by the deformed spring. In the similar fashion here, so that the CQ times x2 dot and minus x1 dot. Okay? And respect to the M2, simply this is a force action reaction, so we simply reverse the directions onto M2 with the same amount here. Okay, so let me not to write again, so that is the same amount with this one. Okay, and now to K3 here, because the M2, this mass block moving in that way, so K3 spring has been compressed. So compressed is trying to rebel, so that force is trying to push back the M2. Okay, the K3 spring has been compressed. So that is the direction of the force applied from a compressed spring to M2 is in that direction. And the magnitude is K3 multiplied with X2. Okay, and the same in the similar way, that is C3 times X3 dot. And on M2, we have again another externally applied loading, and that is called F2. Okay, so that is a free body diagram, and this one using Newton's second law, that would be equivalent to M1 x1 double dot, and this one will be equal to M2 x2 double dot. Okay. So we take the summation M1 x1 double dot will be equal to all the forces, take summation together. And on M1 in total we have 1, 2, 3, 4, 5 terms of the force. Okay, so that is we sequentially write it out. Minus x1 and minus C, sorry, this is C1 here. C1 x1 dot, and then minus K2, x2 minus x1, and minus C2, x2 dot minus x1 dot, and plus F1. Okay. So basically here the 5 terms here, and the similar way here, and m2 x2 dot dot equal to I made a mistake here. Any mistake? I think the sign, right? Because the 2 forces in the same direction of the inertial motions. Okay, so now for this one, starting from here is minus k2, x2 minus x1, and minus c2, x2 dot minus x1 dot, and this one minus k3, x2, and minus c3, x2 dot, and plus f2. Okay. So put everything together, and that is the equation. Let me write it up here. So let me move in m1 x1 double dot plus c1 plus c2 x2 x1 dot minus c2 x2 dot plus k1 plus k2 x1 minus k2 x2 equal to f1t. Long writing here. Then the second equation is m2 x2 double dot minus c2 x1 dot plus c2 plus c3 x2 dot minus k2 x1 plus k2 plus k3 x2 equal to f2. Okay, so that is the 2 equations. And now again, based upon this, I want to exercise and put this form into the matrix representations. The reason why we can kind of keep practicing, because later on part of our calculation will based upon the matrix form. Okay, we're going to apply the linear algebra, so we have to start with the matrix form. So let me write it up. Here is a 2 degree of freedom. So let me write it up the patterns first. And this one. So basically, this is a representation of the matrix multiplied with a vector. Once we implement it, for example, here we have, say, like we did last time, ABCD multiplied with XY. Okay, basically, we implement it is in this way, this row multiplied with this column, and that will give us, for example, if this is the, say, the alpha beta, okay? So basically this row will multiply with that column and will be equal to alpha. So basically that gives us is ax plus by equal to alpha. And then the other one we implement is in this one. CD multiplied with this one equal to beta. So cx plus dy equal to beta. So basically, this is the expressions of the 2 set of equations. So if we reverse the process to this one, basically 2 equations with combined with the more than 1 independent variables, we can reverse the process, put it into the matrix form. Okay. So keep this as a reference. We can try to how to do this. The first one, we look at the double derivative, the acceleration terms here. So here for the first equation will be lined up on the first row of the column. So when we transform the first equation, you simply focus on the first row of each matrix. So this one is n1 times x1 double dot. So for the first row, we have two elements here, multiply with the two things. So here is n1, we're going to come to here. And multiply with 0 without the extra double dot in the first equation, so that put into 0. Okay, if you capable, do it right away, and you can double check. Now we come to the velocity terms. For the velocity terms, again, that is the operation of the two elements multiplied with the x1, x2 individually, right? So this one, we look at this one here, that is the coefficient C1 plus C2 multiplied with this one, so that is the C1, C2 come to here. Come to as the first element. If you compare this one, you can see that right away. Now for the second one, this one multiplied with C2, and that corresponding is minus C2 here. Okay, so that is minus C2. So that is the element 1, element 2. Now for x1, x2 in the similar fashions, and that is k1 plus k2, and this is minus k2. Are we okay? So let me use a parenthesis to indicate that is one element. Are we okay? Should be straightforward. So let me here quickly write it out. So that is C2 minus C2, and this is C2 plus C3. So that is minus K2 and K2 plus K3. Okay, so that is the way we come up with this. And here is a definition. Again, we talked about this last time already. This one is called the stiffness matrix. Not stiffness, mass. Okay, and this one about the spring, so we define it as called the stiffness matrix. And this one is about the damping, and that is called the damping matrix. Those are just the terms used for communications. And this one basically we call it called the force vectors. Okay. And if you like, you can further define this called the displacement vectors, etc. This is velocity vectors. These are acceleration vectors. Okay. So right now you can see for multiple degree freedoms, if we would have say 3 mass blocks, then you should imagine this vector should expand into 3 elements, right? And then the corresponding matrix will be expanded into 3 by 3 rather than 2 by 2. If we have more than 3, say n number of the mass blocks, then the content will be expanded accordingly too. So that kind of give us a hint, and always every year always like this. But kind of give us a hint. Now it will be the good time to use program to help you to do the number crunching, which means do the calculations, just because due to the huge amount of the numbers here. Okay, and then either any program, Excel, MATLAB will be the best one, because MATLAB, the essence of the MATLAB basically is to deal with the linear algebra, and that perfectly fit into this one. Okay. So that is the first note. The second note is this. One qualitative point for you to check whether your derivation is correct or not is this. All the mass matrix, damping matrix, and stiffness matrix, if you're doing things right, then they must be symmetric. In other words, if you would find any of the 3 matrices you derive is not symmetric, then you made a mistake. Okay, so this is a qualitative check for you. And what is symmetric later, I will give you the preview, and hopefully you also have read the the emails, so you have really review of these things. So here we've done the equation of motion. I want to move on to new topic. Before doing that, 5 seconds for any question here.